This is a question on DC machines. So a DC machine driven at a speed of 1170 RPM. The open circuit voltage VA versus the field current IF table is given. So you're given the open circuit voltage values for different field currents, and the field current is in amperes, and the open circuit voltage is in volts. So here it is in volts, and the field current is in amperes. What do we need to do with this given information? We have to calculate the torque that the machine will develop at a field current of 0.7 amperes and at an armature current of 25 amperes. So what we have learned so far, first of all, so here we're gonna solve this question. So we're looking at the field current for 0.7 amperes. First we will look at the table here. So IF 0.7 amperes corresponds to the open circuit voltage of 303. So that's your armature open circuit voltage, and the armature open circuit voltage basically equals to E under open circuit conditions. So this equals to 303 in volts. And with that E value, we will use the expression E equals to K phi omega in order to solve for K phi, and then we will use that K phi in the torque equation in order to calculate the developed torque. So from here, K phi equals to the 303 corresponding to 0.7 amperes of the field current divided by the speed. So this table is at 1170 RPM. Okay, but here we have the speed in radians per second, so we need to convert 1170 RPM to radians per second. So that's why we divided by 9.55 as a constant number. So that is coming from 60 divided by 2 pi. K phi is 2.47, and units you can write volt second. Now from that, the developed torque is going to be K phi IA, so it uses the armature torque. So K phi calculated is 2.47. The armature current we said is going to be at a situation of 25 amperes. And that gives you the developed torque value of 68.1, and the units, the standard units for the torque is Newton meters. So here the main thing to pay attention is that under the open circuit voltage, or this is also called no load state, so there you have VA equals to E. So that's the most important thing to notice. In general, that is not how they are true. There's when it's not open circuit or no load condition, so then you're going to have certain amount of armature current flowing, and under that situation VA, which is the terminal voltage, is not going to be equals to E, which is the induced armature voltage. Okay. Okay, so in this question, a permanent magnet DC motor produces a torque of 8 Newton meters with an armature current of 10 amperes. So the things to notice are, so you have a torque produced of 8 Newton meters from a current of 10 amperes, and that's with an armature current, with an armature current of 10 amperes. And then you have another situation where you're given the armature resistance anyways independent, but the other situation is if this motor has to drive a mechanical load which requires a torque, another value of the torque at a certain speed. So 8 and 20 are two different situations of the loading. So if this motor is to drive a mechanical load requiring a torque of 20 Newton meters at a speed of 1800 RPM, what must be the voltage applied to the armature terminals? First of all, it's a permanent magnet motor, so it do not have any field side, okay, only the armature side, and it is a motor. Where does it states the motor? So for a motor, this is how its equivalent circuit looks like on the armature side, okay. So I'm going to draw the armature resistance, the armature inductance, and the induced voltage. And here are the external armature terminals. So here is the voltage VA, and this is called armature terminal voltage. Okay, This is the resistance RA, which is given to us 0.16 ohms. and this is LA, and under steady state conditions its value is considered as 0, so it's a short circuit. And this is the armature induced voltage E, and that's VA. And the most important thing is the direction of the current. So in case of a motor, the motor withdraws current from the armature terminals into the motor. So that's the direction of the armature current. And what are we looking for? We're looking for the voltage applied to the armature terminals. So this is the question to solve, VA. So VA is given to us as VA in case of a motor is E plus IA RA. So this equation is clear based on our lessons. So this is the direction of the drop across RA. So this is the drop IA RA. So you can see minus 2 plus, plus 2 minus, plus 2 minus. So VA equals to E plus IA RA. And our question is to find VA. So do we know E? Do we know RA? Do we know IA? Let's see what do we know and what needs to be calculated. E, pretty sure we don't know it needs to be calculated. IA under this situation is also not known. What is known is the 20 Newton meters of the torque. So IA is also not known. The value of the RA is 0.16 ohms, so I'll have that there. So in order to calculate E and IA, one situation which I know is, so the equation for the torque is K phi IA. One situation is 8 Newton meters of torque equals to K phi with an armature current of 10 amperes. So I can know the K phi constant value for this motor. And that gives 8 divided by 10, so 0.8, and the units are volts second. The second situation you have is, let's say I write the equation T2 equals to K phi IA2. Now K phi remains constant in this case because it's a permanent magnet motor. So whatever is the field, it's the same field forever. So T2, the second torque equation is 20 for 20 Newton meters. K phi is 0.8, and IA2 under that situation is not known to us. So we can calculate IA2 for 20 Newton meters of the torque and 1800 RPM speed. 20 divided by 0.8, and that gives us 25 amperes of the current. So this IA2 is basically the current IA, okay, 25 amperes. So then I'm gonna say still my E is left. So E equation, everybody is known, K phi omega. So K phi 0.8, and the machine is running at 1800 RPM speed. So 1800 RPM converted to radians per second again, and this gives you 150.8 in volts. Finally, your armature terminal voltage, which is in the question to determine, is E is known plus IA is calculated as well, IA2 multiplied by RA given to us in the question. So, and once you complete the calculation, it gives you a numerical value for the armature terminal voltage as 154.8. Okay, this question is related to the previous problem. So it's the same machine that has to drive a load that requires a torque. So the load characteristics, load torque speed characteristics are such that the torque is proportional to speed. So if I'm gonna say for load, I'm gonna say torque is proportional to speed, or I can say torque equals to A is any constant times the speed. So this is for load. 1 point on the mechanical torque speed relation is 16 Newton meters at 400 RPM. So one of the points is given. We can use that point to give us this proportionality constant. If the armature terminal voltage, so that's again VA, is given as 50 volts, at what steady state speed will the load be driven under these conditions? So first of all, we will make use of the point 16 Newton meters of torque equals to the proportionality constant multiplied by 400 RPM converted to radians per second. So that will give you a proportionality constant, and you calculate this as 0.382 volt second again. So that means for load, the torque speed characteristics are torque equals to the constant 382 times omega. So that's for load. Now for the DC machine, we have the torque speed relationship or characteristic equation given as omega equals to VA divided by K phi minus RA divided by K phi square multiplied by torque. So we're looking for the steady state speed corresponding to armature terminal voltage of 50 volts. So omega we need to calculate. This is given as 50. K phi, you remember, since this is related to the previous question, so K phi in last problem is calculated as 0.8. So RA was also given 0.16 in the previous problem, so I'm going to use that as it is. Multiplied by the torque. So torque, what I'm going to do is I'm going to take this apart as it is and substitute in place of the torque in there. Okay, so I'm going to say torque is 0.382 omega. Okay, so this whole thing goes in there. And you can see this is not a quadratic equation, it's a linear equation. So you're going to combine the omega terms together, and it's only one equation, one unknown. So you solve for omega, and once you solve for omega, omega comes 57.1, and omega is in radians per second. And you can definitely always convert this to RPM. So you're going to say 57.1 multiplied by 9.55, and that gives you N, the steady state speed of the machine to drive this load with the 50 volt armature voltage. So the speed it's going to run at to drive this load is 544 RPM. Okay, this is again a question for DC motor. Okay, so it's a DC motor. And in this case it is not permanent magnet type, so you have the field side and you have the armature side. Okay, and in order to draw the circuit diagram, this is where your let's say armature is, and it is a motor. So these are the armature terminals, armature terminal voltage VA, and that's the current drawn from the terminals into the machine, and this is 0 and this is E. And similarly you can have a field side. Now I have just drawn separately excited machine, but at the same time if it is not stated, so I'm okay, because I'm only analyzing the armature side anyways. So this is the field resistance, and that's 0 again under steady state conditions. Okay, so this part will give you K phi somehow. Okay, so what we're going to do is first part A, we need to determine the armature current. So IA needs to be determined if we are given the load torque. So we're going to say T equals to K phi IA. Okay, so IA we need to determine, T we know the required is 420, and K phi we will see based on some other given conditions. So in order to calculate K phi first, so let's make use of the equation omega equals to, so this is the torque speed equation for the machine, VA over K phi minus RA over K phi square times the torque. Okay, and you are also aware that it's given that we're gonna assume that the motor the losses, all losses being ignored, and one of the losses happens in this resistance RA. So since we're ignoring all the losses, we're going to assume that this value is 0. So that's how we're going to have IA squared times RA loss equals to 0. So with RA being 0, this goes out of the picture, and what you end up having is you're going to have omega equals to VA over K phi. Okay. And again, another thing is, since in this case you can see that RA is 0 in here, so as you can see RA is 0, so this point is exactly same as this point, and this point is exactly same as that point. So with RA 0, you also have VA equals to E as well. Okay, E as well. So that's the basically that is what the equation for E as well, right? E equals to K phi omega. So it's the same equation. These two are the same equations. So let's make use of whatever is known to us. So do we know the speed? Yes, it's going to run at 1600 RPM. So I'm going to say 1600 RPM, and the armature voltage is going to be 600 divided by K phi. So this is where you will calculate K phi, and the K phi calculated value is 3.58 in volts second. So now you make use of that. So you're going to say 420 Newton meters of torque equals to 3.58 times the armature current. So armature current required in order to run a load of 420 Newton meters, its value is coming as 117.3 in amperes. Okay, that's the first part of the question. Second part of the question, part B, is looking for a speed of the machine as 4000 RPM, and the armature voltage is limited to E, or same as VA, is limited to 600 volt maximum value, and we're looking at the field weakening method. Now everybody should be clear about field weakening method. So field, once you will make any change on this part, okay, on this part, on the field side, the change you will observe is going to be for K phi. Okay, so K phi, you're gonna see a change in K phi's value, and since this is a field weakening method, so you're looking at the new value of K phi is going to be lower than 3.58. So what we can do about it? So what we're gonna say? We're gonna say E equals to K phi new value times omega equal, and so E is 600 volt equals to K phi new value, and the speed we're gonna run the machine now on is 4000 RPM divided by 9.55. So this is gonna give you the new value of the K phi, and the new value is coming as 1.43 in volt second. Now we can make use of that new K phi, reduced K phi, with the field weakening method, and we can see how much torque this machine can run. So we're looking at determine the torque available at maximum speed, which is 4000 RPM, if the armature current is not to be exceeded as we have determined in the first case. So armature current should not exceed 117.3, should be same, times IA. So K phi new is 1.43 multiplied by the current should not exceed 117.3, and you got it as 168 Newton meters. Now the thing to observe is the machine power remained the constant in the two situations, meaning the power is given by torque times omega times torque. So if you look at the first situation, let's circle. What is the value of the torque? The value of the torque is 420. What is the speed? The speed is 1600 RPM. So if you do 420 times 1600 divided by 9.55, you're gonna see whatever amount of power you're getting, you can get the same amount of power if you do torque as 168. So let's circle this with the green. Torque as 168 multiplied by the speed it's running at 4000 RPM divided by 9.55. You're gonna see in both cases the power remained constant. So here in the second part, the speed is higher, but the torque is proportionally lower. This is what happens in case of the field weakening method. Okay, so this question is for a 10 kilowatt, and first of all, I want to say that it's for a DC shunt motor. Okay, it is a motor. So the shunt motor equivalent circuit looks like this. So you have the armature side, and this is where the supply comes from, and both the field winding and the armature winding are connected from the same source. And this is your external supply, you can say. Sometimes we call it T, the terminal voltage. Now this terminal voltage is same as VA, and it's the same as VF in case of shunt motor. This is RF, and this is again the same explanation. 0 under steady state, 0 under steady state. That's RA, and this is the induced armature voltage E. So let's say the machine can withdraw a total current of IT from the supply, and that's split into IA and IF. So in case of shunt motor, shunt configuration, VT equals to VA equals to VF, and also the total current IT equals to IA plus IF. Anyways, that's independently true. Now what we have is we have the rated values. So the rated values are 10 kilowatts power, 230 volt is the supply voltage. So this is 230 volt, which gives you VA as 230 volts too. And the rated speed of the machine is 1800 RPM in N. The armature has a resistance of 0.25, so that will remain constant unless there is external resistance added. And we're also saying the rotational losses of the machine. So the rotational losses of the machine are given to us at constant at 600 watts. Watt, W. So W is the units of the power or the units of the loss as well in watts. The field resistance is adjusted until the machine runs at no load speed of this. So you're given N no load as 2000 RPM. So what happens under no load? First we need to understand. So at no load, the machine do not run any load. So that means at its shaft, it does not provide any torque. So the overall torque developed by the machine is going to be only the loss torque. Because nope. Because the developed torque is the shaft torque plus any losses it has to take care of. Since under no load conditions, the shaft torque is 0, so the developed torque by the machine should only be sufficient to take care of the losses. Okay. So in order to calculate the loss torque, we're gonna say we're gonna use the expression P equals to T omega applied to different parts. So T loss is going to be the power loss divided by the speed. So the power loss is given to us as 600 watts divided by the speed the machine is running under this condition is 2000 RPM. Okay, converted to, of course, radians per second. So T loss has a constant number, and it says constant rotational losses may be assumed constant for different speeds even. Okay, so this gives you the loss torque as 2.865 in Newton meters. So that gives you the developed torque as 2.865 Newton meters too, because the shaft torque is 0. Okay, so what are we looking for? We're looking for now what is the speed when the machine drives a load which requires 85% of the rated output torque. First, let's see what is the rated output torque. So T rated. And we'll make use of the same equation, P equals to T omega again. So we're going to say P rated divided by omega rated. Okay, so the rated power is 10 kilowatts, so 10,000 watts, divided by the rated speed is 1800 RPM, 9.55. Do not forget about that. And this gives you a rated torque of 53.05 in Newton meters. Now we want 85% of the rated torque. So we want to determine the speed when the load needs to be fulfilled at 85% of the rated torque, which gives you 0.85 times 53.05. And we calculate the rated torque as at 85%, 48 Newton meters. Okay, so that's the load torque, or that's the shaft torque we want to see. Okay, now when we're going to make use of this equation saying omega equals to VA over K phi minus RA over K phi squared times T. Here this T, make sure, is the developed torque. Okay guys, so always keep that in mind, is the developed torque. So first thing is, it looks like we need to calculate the K phi value, and then we can make use of the K phi and have the developed torque saying what it comes to, and then we can calculate the speed it's running at. So first we will use where speed is known. We'll know a situation where speed omega is, let's say, 2000 rpm. Okay, so we'll calculate k phi based on that. So 2000 divided by 9.55 equals to VA is constant 230 divided by K phi is unknown minus RA is 0.25 K phi square times T developed. Now for 2000, which is the no load speed, for the 2000 RPM no load speed, so T developed is only T loss, which we calculated as 2.865. Okay guys, so we gotta make sure that they are corresponding, so you're not getting any other T. It's the T developed under the situation that we're using the speed as 2000 RPM under no load situation. So you can see that it's one equation and one unknown, but this is going to be a quadratic equation. Okay, and the K phi we calculated from this quadratic equation, and the one which is useful is 1.095 Newton meters per amperes, and you saw it using as a volt second as well, and that's fine too. Okay, so we calculated K phi. Now we know K phi, and we can calculate this omega for this situation. Okay, so let's see what we gotta do now. Okay, so the situation is, one is the speed is 2000 since I wrote omega, so I'll just say it's in radians per second, and here you have the developed torque equals to the loss torque only. One situation was that. The second situation is we're looking for the speed to have a load torque, which is the shaft torque of 48 Newton meters. Okay, so I'm gonna again write the same equation. So V omega equals to VA over K phi minus RA over K phi squared times torque developed. So keep in mind this is the developed torque. Okay, so first let's see what is the developed torque for this new situation, because now the shaft torque is not zero. So developed torque for this motor is the shaft torque plus the loss. The shaft torque, we said 85% of the rated, plus the loss torque is the power loss of 600 watts divided by the speed at which it is happening. So we don't know that. So this is watt, okay? Because the power losses remains the same. So I'm going to substitute. This is your T developed. Okay, and I can make use of this whole equation in here. Then I'm gonna say omega equals to VA, which is 230, and we calculated K phi as 1.095 minus RA is 0.25 divided by 1.095 square multiplied by this whole torque equation. And you're gonna again see that this is gonna give you a quadratic equation, and the quadratic equation is simplified into omega squared times 200 omega plus 125.1, and you can calculate the value of the omega. And the value of the omega which is useful, or which we're keeping, is 199.4 in radians per second, and in N is 9.55 multiplied by 199.4, 1904 in RPM. Okay, so this question is for a series motor. So I have drawn the series motor configuration, and in case of series motor, you guys are aware the total supply voltage is supplied to both armature and field, and the total current IT is same as whatever flows through the armature is same as whatever flows through the field. Okay, so what are we going to do in this case? A load which requires a constant torque of 30 Newton meters, constant torque, is driven by a series motor from a 200 volt source. Okay, 200 volt source. the combined resistance of the armature and the field, so both resistances combined together, RA plus RF, you have it as 0.3 ohms. When tested at standstill, the motor produces a shaft torque of 10. So we are aware that standstill means the speed is 0. The motor produces a shaft torque of 10. So for a series motor, we have the equation a little modified than how it is applied to the shunt and the separately excited machine. So torque equation is K prime IA square. Okay, so the torque is 10 and the current is 25, so we can calculate the constant of the series motor, which is 10 divided by 25 square, and this gives you 0.16 Newton meter per ampere square. That is what its units are, right? The torque is in Newton meter, and it's the current square I square. So that's one part. The other part is the motor. Further tests show that the motor has negligible magnetic saturation, so that means the linearity of the magnetic structure is there up to a current of 50 amperes. So we're good with up to 50 amperes. We need to determine the speed at which the load is driven now. Which load? So the load now, we're looking for 30 Newton meters, T1 or T prime, let's say. Since there is a magnetic linearity, so we know that T prime to T is proportional to IA square. So it's going to be IA prime, let's say, square divided by IA whole square. Okay, so this linearity is true. Or what is known and what are we looking for? T prime is known 30, T is known as 10, IA prime is not known to us. So IA prime square divided by IA is known, 25 square. So one equation, one unknown again. So the value of the armature current with a different load of 30 Newton meters is 43.3 amperes. That's one thing. The other thing, we're still looking for the speed, which we'll see how to find. So again, another equation for the DC series motor is E equals to K prime IA times omega. Okay, so we're looking for speed. We can say that omega is going to be E divided by K prime, which is 0.016, multiplied by, now this is the IA prime actually, okay, which was calculated 43.3, and it is below 50, so we're good. Now where will the E will come from? So E in this case is V, the total voltage, which is VT actually, minus RAIA minus RFIA. So drop across both the registers. So I'm gonna, since and here it could be IF, so what I'm saying is, do not get confused. So here this could be IF, but since IF is same as IA, so I have just replaced it with IA. I can combine RA and RF into one, and I can take IA common, and this is IA prime. Okay, and the motor is supplied from a 200 volt source, so this is 200 volts. Okay, I'm gonna say that's 200, and the combined resistance is 0.3 multiplied by the armature current is 43.3, and so all are known. So E will be calculated as 187 volts. So that E will be used here. So this is 187 now, and you can calculate omega. This gives you 269.9 in radians per second again, and you multiply it with the 9.55, and you got it N in 2578 in RPM. Okay, so that's the DC series motor. So that's the speed, the load, the 30 Newton meters load is going to be driven at. So pay attention to the magnetic linearity. So you can only use this if there is no saturation. So we're neglecting the saturation, or another way of stating the same fact is that there is a magnetic linearity of the structure. That is how we will be able to make use of this situation.